Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on simultaneous equations and inverses. So let's look at a simple example of simultaneous equations. So here we have two equations and two variables. You could probably solve this other ways, like using the elimination or substitution method, but we're going to take a look at using matrices to solve this. So you've already seen before that we can put the coefficients into a matrix. What we were doing in the earlier part of this course was using row reduction, but now we're going to look at setting up a matrix equation. So A is the matrix of coefficients. Call X, that'll be the vector of the things we're trying to find, x1 and x2, and B will just be the two sort of answers, 0 and 11. So if A, X, and B are set up as they are here, matrix multiplication means I can write this equation as AX equals B. A is a matrix, X and B are the vectors above. So when we have a matrix equation like this, we're probably thinking, okay, we want to get X by itself, so let's get rid of A, and of course we've seen in previous videos we can do that by multiplying each side by A inverse. So if I want to get rid of A here, I need to multiply at the start. I need to pre-multiply each side by A inverse to get rid of the A. So of course the A inverse and A just cancel each other out. They equal I, and I times X is just X, and that's just equal to A inverse of B. So that's a quick way that we can solve this system of linear equations, because A inverse in this case is really easy to find because it's a 2 by 2 matrix. So remember, the inverse of a 2 by 2 matrix like this, it's 1 over the determinant, which is 3 minus 8, 11, and then you switch the entries on the main diagonal and you change the sign of the other two entries. So that's A inverse, and we just times that by B, and you should get 4, 3. So that is x1, x2. So the first number here, x1 is equal to 4, and x2 is equal to 3. How easy is that? So hopefully we're asking a few questions here. Well, what if A doesn't have an inverse? So remember when we were doing row reduction that the system of linear equations here, it is inconsistent if when we row reduce it, we end up with a row of all zeros. So that inconsistent could mean either that there are infinitely many solutions or there are no solutions. So remember what we've learned in the invertible matrix theorem is that any matrix, I should say square matrix A, is row equivalent to the identity if and only if it's invertible. So if A is invertible, when we reduce it, it'll look like the identity matrix. So when we were doing row reduction, that means we'll have something like this. This is an example of a 3 by 3 matrix, and in row reduced form there'd be numbers here, numbers here, numbers here. So the first variable just equals that number, second variable equals that, and third variable equals that. But if A is not invertible, you can't row reduce it so it looks like this, the identity, and then you can't use the process that we've just gone through. So when the matrix of coefficients is not invertible, that is when you have a system that is inconsistent. Either there are infinitely many solutions or no solutions. But if A is invertible, we saw in the invertible matrix theorem that AX equals B will have a unique solution X for each B in Rn. And in this case, that solution X will just be A inverse of B. So remember, in order for A to be invertible, its columns which means also its rows must be linearly independent. So that means none of the equations can be linear combinations of any other equations, because then they'd be giving us the same information. If we look at this example here in yellow, you can see that this equation here, the coefficients are just scalar multiples of the one here. If we know what 2x1 plus 3x2 equals, then we already know what 4x1 plus 6x2 should equal. So if that in fact does equal 16, if we double it, then there will be infinitely many solutions, because those two equations are telling you the same thing. If it's not 16, then there will be 0 solutions. And of course, if we were to try to put the coefficients in a matrix, we get 2, 3, 4, 6, and the determinant of that matrix is 12 minus 12, which is 0. And a matrix with determinant 0 is not invertible. So I couldn't use the process I used on the first example here, because the matrix of coefficients is not invertible. So when the number of equations is equal to the number of variables you're trying to find, the coefficient matrix will be a square matrix. So you will have a unique solution as long as the columns or the rows are not linearly dependent, as long as they are linearly independent. So if you had a different number of equations and variables, then you might or might not get an inconsistent solution, and that's what we're going to look at now. So if the number of equations is less than the number of variables, you have something like this, an equation x plus y equals 12. So there's only one equation, but two variables, and we know that this will have infinitely many solutions. If I were to add another equation but add another variable as well, there are still infinitely many solutions to this equation. You will always end up with a free variable. So if I put this into matrix form, I get this one here. But the thing is, if I have here 3 columns but only 2 rows, it's always the case that one of those columns must be linearly dependent. And of course, in this case, you can see the third column can be obtained by taking the first column and subtracting the second column. And that's the issue here and why we always have a free variable. So let's look at the opposite case where we have more variables than equations. So now if you have the number of equations greater than the number of variables, because each equation is a different row and each variable a different column, your matrix would have more rows than columns. So you might have something like this, x plus y equals 5, and let's say 2x plus 3y is equal to 13. So this has 2 equations, 2 variables, and it has a unique solution. In this case, x equals 2 and y equals 5. But if I add another equation, it has to be consistent with these two, because these 2 equations already give me enough information to solve for x and y. So if I make another equation like 3x minus y, so that would have to be, in order to be consistent with the other ones, that would have to be 3 times 2 minus 3, which gives 3, if it's to be consistent. So the point is, if I were to draw up my matrix of coefficients, I just get 1, 1, 2, 3, and 3 minus 1. But again, because there are more rows here than columns, one of the rows must be linearly dependent. It turns out here that this third row is 11 times the first row minus 4 times the second row. So if I were to row reduce the matrix of coefficients, I would end up with a row of zeros. So that would be okay in this case, because I don't need that. I really don't need that third equation because I've got enough information from the first 2. So in that case, it would have infinitely many solutions. But if I change this 3 to any other number like 5, this solution would be inconsistent. There would be no solutions. So as you can see, problems arise when the number of equations and number of variables aren't quite equal. And remember, of course, that only square matrices have an inverse. So that's why we're sticking mostly to situations where the number of equations equals the number of variables, and therefore the matrix of coefficients is square. All right, the last thing I need to show you on this video is another way to solve by hand simple simultaneous equations called Cramer's rule. So Cramer's rule is a way that we can calculate directly each variable in a system of linear equations. So here we call the variables x1, x2, x3, all the way up to xn. If you're given an equation where it says, x, y, and z, you can call x1x, x2y, x3z, so on. So the formula for calculating each of the variables is here, and it involves determinants. So A, X, and B meant the same as they did a couple of slides ago. So A is the matrix of coefficients, B is the vector of solutions, and X will be the vector that contains all the variables x1 to xn that you want to find. So here we introduce this new notation. AI of B means you take the matrix of coefficients and you replace its ith column with B. So A1 of B means you replace the first column of A with B. A2 of B means you replace the second column of A with B, and so on. So let's look at an easy example. So let's solve these two equations here using Cramer's rule. So first we set up our matrices A and B. So let's go through and calculate. In this case, we need to calculate x1 and x2. So to do that, we need to find A1 and A2 of B. So to find A1 of B, I take my matrix A, but instead of writing the first column 1, 3, I replace it with B, so minus 4, 79, and the second column of A remains the same. And then I do similarly for A2 of B, except this time first column of A is the same, and I replace the second column with that of B. When I have these, I can calculate x1 and x2 directly. So x1 is determinant of A1b over the determinant of A. So the determinant of A1b is minus 16 plus 3 times 79, which is 237, so I end up with 221. Now, determinant of A is 4 times 1, which is 4, plus 3 times 3, which is 13. So x1 is just 221 divided by 13, which gives me 17. So x2, I find the determinant of A2 here, so it's 1 times 79, plus 4 times 3, which is 91, over determinant of A, I already calculated, was 13. So the solution here is x1 equals 17, x2 equals 7. So that was pretty easy. So the advantage of Cramer's rule with regard to what we're doing here is you don't actually need to calculate the inverse of A. A needs to be invertible so that this part, the determinant, will be non-zero, but you don't actually have to calculate the inverse. So these are just ways for you to understand, the usefulness of matrix inverses. We can use Cramer's rule or matrix inverses on small matrices, 2 by 2, 3 by 3, and so on. Of course, if we're getting up to 4 by 4 and 5 by 5, calculating the inverse is really hard to do by hand, so Cramer's rule would be better. But I do want to point out that in most settings in the real world, if you're dealing with really, really large matrices like 50 by 50, you wouldn't use Cramer's rule or inverses because determinants and inverses are computationally very expensive. They require so many operations to calculate. You'd tend to use other methods like row reduction. But I wanted to show you this method because they're really handy and quick if you need to solve simultaneous equations of small matrices. All right, this has been the luckiest maths teacher in the world. Have a great day.